And then this is yes, thank you. Okay, so we'll mostly we'll be going over like some basic things in linear algebra. We will start off with this definition of a field and then some define a vector space, and mostly we'll be talking about the dimension of vector space, like how that is defined and why it is well defined. Okay, so yeah, this is the definition of a field. Like it's just a field is just a place where you can add and multiply nicely. So all the usual conditions hold. Disclosure is not strictly necessary, right? I mean, it is necessary, but you don't have to write it usually because you say that there are binary operations on the field itself. So yeah, all the usual conditions hold. You can do algebra in the usual way. So yeah, fields. Examples of fields are reals and complex numbers, rationals. Most of the usual things are fields. Also, you can look at FP, which is 0, 1, 2, P minus 1, and addition and multiplication are mod P. Wait, what happened? Did the recording stop? I heard some.
No, like I rejoined.
Okay. So yeah, I mean, usually like all the standard things will hold in a field. So for instance, you can do like polynomials make sense in fields, and the sorts of things you can do, like all the polynomial all the operations will make sense. So also you have this thing called a vector space over a field. It's set V and there are two operations. So you can add, and then there is this thing scalar multiplication, which you can do. So you can add two vectors within the field, such that these things hold. And also scalar multiplication. So you can take a vector and scale it by a element of the field, lambda. So yeah, some things it needs to satisfy that it should be like should satisfy this thing. And distributivity. And also like this thing is necessary because otherwise you have this fairly trivial thing which you can do is that lambda v is just 0 for all of them. For all lambda and for all v. And you can have like degenerate cases like that. So just to make sure that it's a reasonable sort of multiplication, we have this. And yeah, I mean, this definition of a field is saying that it's a abelian group over addition and multiplication if we remove 0. And this is saying that the vector space forms a group with addition and a commutative group. Okay.
What is an abelian group again? Can you repeat?
Okay. Yeah. So also I forgot to ask. Like, do you know what a group is in general?
Slightly, yes.
Yeah. Okay. It doesn't matter either way. It's like just these axioms. Yeah. No, not this last thing. These three things. So like a times b, you have this notion of multiplication, and then you need to have an identity element. Okay, so usually for groups you say multiplication, but like you have some identity 0, and then abelian just means that it's commutative. So in usual groups you don't have this commutative.
Okay.
You have
Okay.
other things. Yeah. Okay. Fine. So we have these things, and also, so now mostly we now need a way to say when two vector spaces are the same, or like two fields are the same. We need to be able to say that. So again, for vector spaces also, like for groups, you have isomorphisms and homomorphisms. Also, like I might just say stuff about groups at any point, but they're not required. So don't worry if you don't know it. Okay, let's see how much of this. Okay, so we have homomorphisms. So like F from B to W. Also, not that a vector space is like it only makes sense over a base field K. Without a base field, there's no real meaning of saying that something is a vector space. So if these two are vector spaces over the same field, then it's a homomorphism if it needs to respect all of the properties. So f of u plus f of v should be equal to f, where u and v are elements in the space. And also it should satisfy lambda times f of v is equal to f of lambda v. Also not that this, like this plus and this plus are different operations. So like this plus is in, so f of u and f of v are elements of w. So this plus is in w and this addition is in v. So they're actually different operations. So like it doesn't, it's a slight abuse of notation to say plus for both of them. You can't exactly do that, but for now we'll just use the same terminology. Like it's fine.
But
But these are different operations.
can't you extend this to also use that over the field? I mean, if you have any vector space over one field and any other vector space on another field, you can just have something between the fields and something between the vector spaces, and then you can say the vector field space, which the field vector space with the field is the same as that vector space with the field.
Okay, sure. Yeah, I guess you could define something like that. I haven't seen any particular use of that, but I guess you could do something like you're saying that you give a function from the base from one field to another field and from the vector space to another vector space.
Yes.
Yeah, sure, you could do that. But okay, so it's okay, interesting. Okay, so one thing is that there's this result. I don't know if homomorphisms from a field to another field are actually that great. So like there's this result which says that every field has a generator or like a primitive
Meaning?
So I'm not sure how that would work, but it's an interesting idea. Like I have a feeling that it might just make it like the base fields be isomorphic. I'm not sure about that, but it's possible, I think. So the point is key, if you have a general field F and then there is this, you can prove that F has a primitive root if F is a field.
What is the meaning of primitive root?
A primitive root is just something which, like if it's a primitive root G, then G square 1 G square G cube and so on, they form F completely. Okay, wait, never mind. No, okay, so yeah, you're right. We could do something like that.
But
This result only holds for finite.
I mean,
Yeah, go ahead. What were you saying? So yeah, you could do something like that. I'm not exactly sure. I haven't seen homomorphisms from a field to another field and how they behave, but I think you could define something like that and it would make sense. Okay, so either way, like this. So basically, it respects a homomorphism respects all of the properties of the base field, like addition and scalar multiplication. Both of those properties it respects. So then F is an isomorphism if it's just a bijection. Like instead of being a general homomorphism, it's a homomorphism and it's also a bijection. And that's it. So we again have this idea that two isomorphic two isomorphic spaces should be basically the same because it's like you're renaming them. If you take U and replace it by F of U, then you're saying that it doesn't, these things just say that it doesn't change how the vector space behaves. And they're kind of the same. And yeah, so we say this thing if there's an isomorphism between them, like V is isomorphic to W, and then like you can quite easily show that this is an equivalence relation just by composing the isomorphisms and so. Okay, so let's see what general things a homomorphism can be like. So it need not be an isomorphism, but so it can if it's injective, let's say. So then also we have some, it's not an isomorphism, but it's kind of similar. So like then if it is an injective function, the homomorphism, then all you need to do is you need to look at the image of that function and then it will be isomorphic to V. So that is there for injective functions. But for general functions, like a way to sort of understand the structure is that we have the kernel and image. The kernel is all the things which kernel of function. This is a general homomorphism from B to W. The set of all people. No. Yeah. So this is just all the things which are mapping to 0. Okay, so this measures like how much it's sort of key if you have a general homomorphism. So all you're doing is you're setting these things equal to 0 and you're modding out by this. That's basically what a homomorphism is doing with the kernel is this. So in particular, what it means is that if you have a general, so first you'll have to define what modding out means formally. So then you have, wait, give me a second. Okay, so if we have, wait, the laptop, give me 1 second, please. Sorry about sorry about that. Okay. So yeah, I was saying ki we were going to see how to mod out by a particular kernel. So like if you have a general vector space V and then you have a subspace, which is just a subset of it, which is also a vector space under the same operations. So V and we need to get W is a subspace of V. And like anywhere if I say V, then it's a vector space. Okay. So then we define this thing called V mod W in W. And what we're doing over here is we're taking the set of all P plus W. So the elements of this set are themselves sets of this form. So V plus W is just key, you take all the elements of W and you shift them by V. So what this definition achieves is that if you have two elements, U and V, and the difference is in W. So like in some vague notion, you want to say that U is congruent to V, like mod W, whatever that means. So that is in fact true because here you have that U plus W is equal to V plus W. And the reason is just key. If you have any element in U plus W, then it's like U plus some element in W. And then what we need to do is we can do this thing minus V. And this thing also belongs to W. Because this thing is in the space and U minus V is in the space. So the whole thing will, so like you can add them up because W is a subspace and it will belong over here. And then if you look at this element, so that also means ki V plus U minus V plus W will belong to V plus W. So the point is ki these two sets are equal, which does the job because if we associate each element, we are associating it with a set and satisfies this property. That it successfully captures what it means for U to be congruent to V. So yeah, you have that function. And this is in fact, this satisfies the usual condition. So like if you look at this function from P to B mod W. So what this does is it is surjective naturally because like W V mod W literally consists of all elements of this form. And it is also, and the kernel of this thing is equal to W. So the point is that in fact all of the homomorphisms are of roughly this form. So like if it's not equal to V mod W exactly, then it will be isomorphic to V mod W. So that is first isomorphism. Okay, it's not exactly. I think first isomorphism theorem is for groups. I'm not sure if it's called that.
What do you mean the homomorphism will be isomorphic to another? What do you mean two functions are isomorphic?
No, I was not talking about the function. I was talking about the image.
Oh.
So like, okay, the point is that if F from V to W homomorphism, okay, so first of all, note that this thing is also a vector space. Yeah, I forgot to mention that. So if you have if you have V mod W and you want to add two elements in it. So all you need to do is you just manually add up all the elements in the set. But I mean, that's kind of hard to do because like, you will have to prove that it's still of the same form. So what we'll do is if you have v1 plus w and we want to add v2 plus w, so then we'll just directly add the elements. And now you just need to prove that it's well defined, which is not that hard. So like we need to prove that for a particular set, there might be multiple choice of v2. So you may choose to represent it as v2 plus w or some v2 prime plus w. And we need to show that whatever happens, this thing is the same. So I mean, that's not too hard. So the point is if these two are the same, so then you'll have like v2 minus v2 prime belonging to w. And then that means over here you'll be adding subtracting v2 minus v2 prime, which is not a problem because it belongs to w. So either way,
Wait,
v
wait.
mod
Can you
w.
please explain once?
Yeah, okay. Okay, so v mod w is a vector space under the following operation. So yeah, v plus w, v1 plus w. Then you want to add plus v2. Okay, so you have this operation. This is the addition over this in v mod w. So yeah, we need to prove that this is well defined. So to do that, what we need to show is that instead of v2 plus w, if you had some other representation of the same set, right? Because this is a set, like it's not given to you in the form of v1 plus w. This might also be equal to some other u plus w. So then we need to show that this set will be the same. That is, if v1 plus w is equal to u plus w, prove that v1 plus v2 plus w. And we need to prove the analogous thing for this one.
Got it.
Yeah, so for this, you just say that, like I said, somewhere over here. Where did I say? Yes, so over here, I said that if the sets are equal, then the difference belongs to W. So like over here, we have that V1 minus U belongs to W. And what we need to prove is that these two sets are equal, which is just saying that V1 plus V2 minus U plus V2 should belong to W. But now, like you said, like I said earlier, vector spaces follow all the usual properties. So we can cancel v2 from here, and we'll get that we need to show v1 minus u belongs to, which is true. So that proves that our notion of addition over here is well defined. And then you also have scalar multiplication, which works in exactly the same way. So we have v plus w. Do you want to scale it by some lambda? Lambda. So what do we need to prove over here to show that this is well defined? Anyway, just speak up. What do we need to prove?
W is a subset of is a vector space of subvector space of V, right?
Yes.
It's a vector space or what? It's just a vector.
Yeah, it's a vector space.
Don't we just have to show that anything? We just take lambda times all the elements of W and
No, like this thing, we're defining it to be like this. Like, we're not scaling the whole set by lambda. We're just defining our scalar multiplication to be like this. And what we need to show is that this is well defined. So like we need to show So what we are given to multiply is we are given
Want
this.
to, if we replace R by any other thing of any other member of W, this works out properly.
Yes, exactly. So we
Hmm.
need to prove that instead of V, if we had some U such that U plus W is equal to V plus W, and then we multiply. So then you'll get E lambda U plus W. So then we need to prove that these two things are equal. That is, we need to prove V. And how do we prove this?
Lambda V minus lambda U should be in W, unless I'm wrong.
Yes. Yeah, exactly. Lambda U minus lambda V is equal to W. Sorry. And this is true because distributive law holds. So this is just lambda times U minus V. Okay, so that means that V mod W, it's a terrible W, is a vector space. So then, okay, now we can probably look at this thing. Yes. Okay, so now it actually makes sense to say that they're isomorphic, because this is a subspace, and okay, also we need to prove a few more things. Never mind. So first of all, we are modding out by the kernel. So we need to prove that kernel is a field, the kernel is a space, is a subspace of V, and image is also a subspace. No, image is just a vector space.
Wait, 1 minute. What is IMF? Image.
Yes, IMF is image.
Isn't image a vector space by definition? It has surjection, right? It's a surjection.
Oh, sure. No, like, what do you mean it's a surjection?
Didn't we define homomorphism to be a surjective?
No. A homomorphism is just anything which respects the structure. It doesn't have to be surjective.
What do you mean by image?
Yeah, so the image is okay, so it's like the set of all values which f of v takes.
Yeah, it is a images vector space because if f of v goes to w and f of u goes to k, then f of v plus w goes to something that is u plus k. Right? If u is a part of image space and k is then u plus k. And similarly, if u is part of it and k is also part of it, u into k is also part of it.
Yes, exactly.
And we can do similar thing for kernel. Because if
Wait,
we have
there is one more thing you need to do. You need to show scalar multiplication also. But yeah, that works.
fields have inverses, multiplicative inverses, right?
Yes, they do.
Okay. So for kernel, we can just do that. If something goes to 0 and something else goes to 0, then the sum must go to 0.
Yeah, sure. And
And
you can also scale it.
yeah,
Yeah, that works. Okay, so this can takes all values in W, all values in the image. And this also, so does this. So like this is anything of the form. Okay, what to do? K plus, no, K is the base field. Okay, A plus B, where A and B are in the image. So then we are saying that A plus B also belongs to image. And then we need to prove the same thing for scalar. Okay, if f of v belongs to the image, that is just true because that's how image is defined. Then lambda times f of v belongs to the image because it's equal to f of lambda. So then we have image is a vector space.
What's that curly sign with the equal to below it?
What can we say? The equal to below it.
You've written V by curve,
This,
kernel of F is whatever.
this, yeah, this is isomorphic. I think I mentioned it somewhere. Anyway, like this just says ki there's an isomorphism between this space and this subspace.
Okay, that's it.
Yeah, that's okay. Okay, now what do we do for kernel? We need to say that f of u plus v is also equal to 0. But that just follows from the fact that f is a linear map. So, okay, a homomorphism is also called a linear map. Where did it go? Yes. So anyway, we know ki f is a linear map, so then we just know ki f of u plus v is equal to f of u plus f of v. 0 plus. So then we know that if u and v belong to the kernel, then u plus v also belongs to the kernel. And similarly, you can prove that if u belongs to the kernel, then we need to prove that lambda v belongs to it. So for that, just need to say that f of lambda v is equal to lambda times f of v. So these things also you'll have to formally prove that lambda times 0 is equal to 0. But it's fine. Like it's easy to show. Okay. Okay, so this proves that the image and the kernel are both subspaces. So now we can look at what this means. So we are saying that you take V and kernel of F is a subspace. Then you mod it out with kernel of F. And we want to show that it is isomorphic to the image.
Is v plus v or equal to lambda v for some lambda always true?
What V plus V? What do you mean?
Is v plus v equals to lambda v for some lambda belonging to f always true?
Oh, yes. Yes,
How,
yes, yes.
how do you prove that sort of stuff? Like how?
Okay, so V plus V is equal to 1 times V plus 1 times V.
Ah,
But then we have distributivity. So this is
oh,
equal to 1 plus 1 times V.
ah.
And 1 plus 1 belongs to the field because 1 is there and you can add.
One is the identity, right? I mean the multiplicative identity,
Yes.
whatever.
Yes. Yeah, 1 is multiplicative. Okay, so how would we go about doing something like this?
Also, Shreya, do you want to maybe give an example of this where we see it happening? For example, like could we consider V as integers over integers? F as something like taking anything to its remainder mod 5 or something?
Okay, first of all, we cannot take V as integers over integers. Integers are not a field. We need to.
My bad, my bad.
Rationals?
Naturals are also not a field.
Rational.
Okay, yeah, rationals are a field. Sure, we can take rationals. So rationals, and what is your vector space?
I take itself rationals and rationals.
Okay, sure, you can do that. So now, yeah, so this is one field. Also, like you can also take rationals raised to n if you want, like the set of all n tuples of rationals. That is also a vector space. Just same. So it's Kind of hard to think of a. Okay, so
How about like you send negative stuff like to positive stuff and
Mm,
positive to
yeah.
positive.
Just
Yeah,
take the
like
just take
absolute
the
value.
integers as kernel. I think no, that won't go.
integers are the kernel.
No, that won't go. No, because if anything is a kernel, then
No, but integers are not a space, no?
yeah,
Because
like
like
just take q square and take anything of the form a comma a as your
okay, that we can do.
that as your kernel.
Yes, okay. So this is our kernel. Okay, so now what is vmod kernel? Okay, so one example could be set just any element in V plus this set.
So does
So-
vector space q square or q to the power n?
No, q square, I think. Yeah, it's q square. I'm just saying that q to the power n in general is a vector space. We are working with this. Okay. Okay, so let's see what I did this kernel of f. So then this is just like kernel of f is the set of all a comma I. Then this becomes all things of the form a plus 1 comma a. A plus 2 rationals. And in general, if you want to look at this kernel, like this space, then it looks something like, in general, if you have like k comma l, you can't use k. Okay, sorry, a comma b, and then we're adding the set of all things of the form lambda comma lambda. So then this is just everything of the form lambda plus a comma lambda plus b. All things of this form. Of course, first we fix a and b. Then we take this tuple and add it to this whole set. This we are adding it to the whole set. So then it would in general look something like this. Okay, so now, okay, so if you want to given the kernel, like if you are given the kernel is equal to this set, lambda, then you want to construct such a homomorphism. Okay, so I think there is only one homomorphism. Not only one, but there is a. Wait, is there only one? No, there are. But there's a fairly nice form. It's just everything of the form a times x minus y. F has to be of this form, such that a is fixed and f sends x comma y to them that fails. Also, like where are you sending? Like this homomorphism is from q square to where? Is it from q square to itself or to rationals? Where is it going?
I think rationals makes.
Yeah, okay. Okay, so another thing is that, so in general, like I was not planning to go there in this class, but anyways. So if you want to nicely characterize all homomorphisms from rationals, from let's say if you want to do from q square to rationals, then all of them are of the form like this and x comma y to ax plus by. So they're all linear in the way you would expect them to be. Their a and b are fixed. And the way to prove this is fairly simple. So you just take the vector 1, 0 and now see where this goes. Let this be A. And then see where 0, 1 goes. Let this be B. And now you can just say that if you have x, y, so then this thing is equal to x, y, x times 1, 0, this y times 0, 1. And now if we take f of both sides, then we'll just get this is x. So first of all, it splits up. So if you want to take f of x, y, then it will become f of x times 1, 0 times 0, 1. Because you can split it like this, it's additive. Then you can also take the x outside because x is a rational, and you can take the y outside over here. Then you get ax plus by for all xy. So this is a pretty nice characterization. Does this make sense?
Yes.
Okay. Okay, sure. Now also let's just see if let's see this thing in action. Like first isomorphism theorem. Then if you have the function which sends x, y to x minus y. Because like you said, you're making all things of this form to be your kernel. Then what is the image of this function? Like what are values? That just says what are values this x minus y take. If x and y are allowed to vary over all rationals.
All rationals.
Yeah, exactly. So this is all rationals. And then what our result is trying to say is that if you take q square and mod it out by the set of all lambda, then this is isomorphic to the set of all rationals. Okay, so first of all, what do all the elements in this set look like? Like I told you earlier, they are all of the form lambda minus the set of all lambda plus e times lambda plus b. So that lambda is varying over all rationals, and a and b are fixed. This is just the random. This is just how an element of this thing looks. So, is this a good way to represent? Like, does this do we really need two variables to capture all of this information?
A minus B.
Yeah, exactly. So you can instead do this is lambda plus a and lambda plus a plus b minus a. Lambda belongs to rational. And again we are fixed. Now the point is key, instead of letting lambda vary over all rationals, we might as well make lambda plus a vary over all rationals. So here, like we can just get rid of the variable a. So it's just all set. So an element of this looks like it's lambda. So we're taking lambda plus a and replacing it with lambda everywhere, because that also takes all rational values. Like lambda, lambda plus b minus a. And now lambda varies over all rationals. B minus a is fixed. So now what is the isomorphism? We have elements which are of the form like the set of all lambda, lambda plus r. Okay, actually instead of representing it like this, over here we'll do lambda plus b. Yeah, never mind. Over here we'll do lambda plus b. Here we'll do lambda plus b plus a minus b. You can see why or something. So now it will instead become the set of all numbers of the form lambda plus r and lambda, comma lambda, such that lambda varies over all rationals. And we want to say this is isomorphic to the set of all rationals. So what's the most natural function which you can think of? Like you
Lambda.
take this.
Just take your lambda.
Or
Yeah, but
take it
lambda is varying. So like this whole set has lambda varying over all rationals. R is fixed.
Yeah, map
Some
it to R.
Yeah, exactly. So we map it to R. And this is a linear map. Like it's an isomorphism because first of all it's surjective because like R can take any rational value. And it's injective because if R is different then if R is then it is, and you can check it is additive because like this extra R term. So if you want to add two things, if you want to add like lambda plus the set of all lambda plus R comma lambda, and then you have the set of all lambda plus k comma lambda. So then like the lambdas will sort of cancel and they will just add up nicely. That is a small exercise. It's not a lot of trouble. So this is the isomorphism. In particular, note that this was our function. And what our isomorphism is doing is it's taking lambda plus r comma lambda and it's sending it to r, which is just, it is equal to lambda plus r for all of whichever lambda it is, it's equal to this. So like in particular, it's sending this map is just f. Not exactly because we are dealing with whole sets over here, but it is taking every element and sending it to f for a particular element. So in particular, I'll just say this formally once. This kernel of f sets isomorphic to image of f. Okay, so our function phi is that which takes an element of a set of the form v plus kernel of f and it sends it to f of v. That's it. And we claim that first of all this is well defined and also it is an isomorphism. Yeah, it's an isomorphism. Is everything clear till here until this point?
Yes.
I'm sorry, but how do you prove that it's well defined earlier? Like, what were we doing?
Okay, so the idea is that we are not really given, so we are taking a function from v mod kernel of f to image. So when we are given an element of this v mod kernel, it's not of this form. We are just given the set. So we are choosing a particular v, and so this is just a representation. This could possibly, the same set could have been represented as some other u plus kernel of, and it could be the same set. So what we are trying to prove is that whichever representation you choose for that set, it should map to the same f of v.
Okay.
Right. So yeah, that's what we have to prove. So if we have this thing, and these two sets are equal, right? So that what that means is that v minus u belongs to the kernel. Okay, whatever. Let's say ki, okay, so if these two are equal, then what we need to prove is that f of v is equal to what will this thing map? It will map to f of u. Will to f of u. We need to prove this. And now let's see what is given to us. We're given that v plus kernel of f is equal to u plus kernel of f.
That means for some, there's some I such that v plus I equals to u.
Yes, I belonging to the kernel.
I love the kernel. And we can just do the f of a plus b equals f of a plus f of b thingy or v plus I.
Yes, exactly. So then and this is because I belongs to the kernel. So by definition, f of anything in the kernel is 0. And now we need to prove that this is well defined. No, we proved it's well defined. We need to prove that it's an isomer. Okay, so why is it surjective?
For any thing in the image, it is a f of k for some k, so just take k plus 1.
Yes, exactly. So it's surjective. Yeah. Okay, that is true. And why is it injective?
We just showed that. No,
I didn't get you. Can you repeat?
we- if u plus curve goes to f of u, and if u plus curve goes to the same thing as v plus curve, right?
Yeah,
Then
so f of u is equal to f of v.
okay, we can say f of u plus j is equal to f of v for some j,
Why?
because v minus u f of
Yes, okay. So in fact, yeah, you're saying that f of v minus u is equal to 0.
yes.
Yes, so v minus u belongs to the kernel, and therefore the two sets are equal. That's correct. Okay, good. So this is an isomorphism. No, we don't yet have it's an isomorphism. We prove that it's bijective. We need to prove that it is a linear map.
It's a linear
Wait,
map
how do we
because
get it surjective again?
Okay, so we're sending v plus kernel of f to v f of v, and f of v takes all the values in the image.
Oh, yes. Okay.
Okay. So now we need to prove that it's surjective, that it's a linear map. So what do we need to prove for that? Okay, fine. So we need to prove that if phi is the function, okay, I said phi is the function. So phi of this thing, we add them, is equal to phi of v plus kernel of f plus phi of u plus kernel of f. And this is what it means by it is well defined. But this quantity, by definition, it is equal to v plus u plus kernel of f. Okay, so we need to learn phi of v plus u plus kernel of f. Okay. Okay, so this is just for by definition, because this thing we know to be like this is by definition equal to f of u v plus u, and this is equal to f of v, and this is f of u. Now we know that they are additive, like f itself is a homomorphism, so then we're done. Okay. running out of time, so I'll not do the scalar multiplication part right now. You can try that later. We'll just move on to the dimension of a vector space. Okay. So first of all, to see what linearly dependent means. So if you have a set S, okay, this is by S and this customer V1, V2, blah blah blah, Vn, which is this is a subset of V. Then we say it's linearly dependent if there exists some scalars, lambda 1, lambda 2, blah blah blah, lambda n, then to V, such that and lambda I not all zero. I mean, all of them being zero would just be trivial. So the idea is that if there is some lambda I which is non-zero, then like assume if it is lambda 1, so then what we can do is we can say V1 is equal to minus of lambda 2 by lambda 1 V2 plus lambda 3 by lambda 2 V3 plus blah blah blah. If this was to be true. And this is basically what it means for it to be linearly independent. That one of them we can write as a linear combination of the others. Okay. Now let's see. What is the span of a set? There's some small definitions you need to know, then I'll move on to some fun stuff about basis. In the span of a, if you're given some vectors in this, then there's just all things of this form. And the lambda are all allowed to vary over the base field. So it's like the definition of linearly dependent and span. I hope it's fine.
Yeah.
Okay.
Wait, what is span again?
All the things which make a linear combination. So the set of all such things, such that lambda I all belong to the base field.
Okay.
Okay. So now let's define the dimension. No, not the dimension. Find a basis of V. So V1 blah 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 Vn, the set, is a basis if it is linearly independent, first of all. Of this. Oh my god. Okay, it's linearly independent and its span. What's the spelling of linearly? Okay. Independent. So it should satisfy all. So nice thing about that is why I mentioned this interpretation of linearly independent is that what it's actually saying is that if they were not to be linearly independent, if they were to be so if they're not linearly dependent, then they're linearly independent. I should have said. So if they're not linearly independent, what that would mean is that there is some element vi among these, which belongs to the span of the other elements. Which makes vi redundant in some sense. So what that would mean is if we have like lambda1, so assume this is v1 itself, just for convenience.
It has to be countable, like your v1, v2, vn.
Okay, good point. Not countable also. For now, we'll be dealing with finite. But
So
in case it's infinite, so for linearly dependent, it doesn't make any sense to talk about infinite sum in most places. So sometimes it makes sense, but not in general. So we will say if this is true for some finite, assuming this were to be an infinite set, then we'd say it's linearly independent if there is some finite subset of it which is linearly. We'd say it's linearly dependent if there is some finite subset of it which is also linearly dependent. And for the case of span, also, if it is infinite, then we'll just take the union of the spans of all of its finite subsets. So we mostly, even when we are dealing with infinite subsets, we are sort of referring to finite cases only.
So for infinite things, we say it's linearly independent if it is linearly independent of a finite number of other vectors.
If any finite subset of it is linearly independent, then we say.
And we can't do something like it is linearly independent if and only if it cannot be written using any of the others. Can't have infinite sums.
Yeah, you can't have infinite sums. So you could say it's linearly independent for every one of those vectors. It cannot be written as a linear combination of a finite number of the others. But an infinite sum would not make sense. Wait, why did I do? Okay. So if we have this thing, v1 belongs to the span of the other things. Like if it were to be linearly dependent. Let me write this. So if it were to be linearly dependent, then what we would have is that v1 is kind of redundant in some sense. So span of this whole thing, all of the elements, would be equal to span of v2 and so on till vn. And the proof is just that if you have an element of this, which is lambda1 v1 plus lambda2 v2 plus blah 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 and vn. So then, but you already have that v1 belongs to the span of the other thing. So v1 is equal to some alpha1 v alpha2 v2 plus alpha2 plus alpha3 v3 plus blah 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 alpha and vn. So if you want to write this as a linear combination of these things, all you need to do is you substitute the value of v1 as this, and then you'll get something in terms of v2 and so on till vn. So now what I'm trying to say is it's linearly independent and it spans the whole thing. So this is also saying, this is actually equivalent to saying that it's the least set, the minimal set spanning V.
Are we sure it always exists?
No. Okay, a finite basis doesn't always exist. And for an infinite basis, I believe there is some axiom of choice kind of argument, but I'm not really confident about axiom of choice. Like, I'm not sure how to use it properly, so I would not vouch for that. So we always will assume it's finite dimensional, meaning that there's a finite basis for most vector spaces, but we don't always need that. Okay, we'll not assume that in general. But for now, suppose it does have a finite base. Okay, so the main result is key for a basis. It is equivalent to this set. The following things are equivalent. That the thing is a minimal set spanning V, meaning that, so notice I said minimal and not minimum. So you're not talking about the cardinality of the set. What you're talking about is that you cannot remove any particular element from it and expect the span to, and say that it will still span V. From V1 till Vn, if you remove any particular element Vi, then it will no longer belong to the span. So it will stop, the set will stop spanning V. And also, okay. For all V belonging to V, there exists unique lambda 1 so on to lambda n such that lambda 1 V. Okay, so we claim that these three are all equivalent to being a basis. Okay, so how do you prove something like this?
You assume that you just move one element
Hmm.
and it is not spanning.
Oh, I have another condition to add on to this.
Okay.
I mean another, yeah. It is spanning, it spans V, and it is linearly independent.
Okay, true. Yeah, I mean that's the thing, basis for condition.
Yeah.
Okay.
Also, do you want to talk about an example of a basis in some vector space?
Okay, true. I should talk about an example. Okay, so the most standard example is that if you have something like r to the n, or k to the n for that matter, then 1, 0, 0, 1 and all zeros, and 0, 1, 0, blah 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 zeros, and so on. These things form a basis. Like for r cubed, it is 1, 0, 0, 0, 1, 0, 0, 0, 1. This thing is the standard basis. But you can also have other things, like you can have 1, 0, 0, 1, 1, 0, 1, 1, 1. So this, for instance, thing is also a basis of R cubed. So you can have anything in general, like as long as. So there's another thing which I was going to prove was that if it's linearly independent and if it has cardinality 3, like equal to, in this case, 3, then it's a basis. So for that, we'll need to prove something else, which is key. The cardinality of all the bases are equal. And also something else we will need. But yes, that's generally how a basis looks. Is this better?
And we do this by saying that if we remove an element and it is still spanning,
Hmm.
That means we could have written that last element as a linear combination of the other elements.
Yes. So it is not a basis.
Yeah.
Okay, now for the other direction.
And if it so yes, if it is spanning and
But so like what you just said, it proves that 1 implies 2. No, it proves that 2 implies 1. No, not 2. Like this fifth condition, it implies the first one. Because if first were not to hold, then 5 would also not hold. That's what he just proved. So now you need to prove 1 implies 5. Okay, it's fine. You might not even need to prove that directly. No, wait, what?
Yeah.
You don't need to prove 1 implies 5.
Assuming it about finite stuff, if it is a basis
Hmm.
and we remove an element,
Yes.
then it cannot be spanning, right?
Yes, because if it were to be spanning, then that element can be written as.
Yes. And if I have to show the other way around, that is what is the other way around. If it is spanning, then it has no, what's the other way around? Inwards.
Or if it's minimal and spanning, then it's a basis. That's what you need to show.
Um, minimal. Minimally
So how would
spanning.
you prove something like that? You want to prove that it's a basis. So you
Yes.
already know that it's
It's-
spanning. You want to
so-
prove that it's linearly independent.
Right. If it was not linearly independent,
Yes.
that means we could represent one element as linear combination of other elements,
Exactly.
and we could remove that element since any, and we could
Yeah,
show.
Okay, so yeah, the proof for one implying 5 is that if 5 were not to be true, so first of all, like spanning condition is there in both. So if it were not to be linearly independent,
What is 4 inwards?
what?
What is 4? Statement 4.
Oh, statement 4 is not there. Sorry. This whole thing is one statement. That every element in the vector space can be uniquely written as a linear combination of these things. Okay, so for 1 equivalent to 4.
If it is maximally linearly independent,
Yes.
then that means that I'll assume it is spanning. Assume it is not spanning. That means that's one element which is linearly independent of it, and that means you can just add it in.
You would have to do a little bit more work, but that's essentially the idea. So
Right?
if
Because
you add it back in and it's not linearly independent, then so because of this, where is it? Yes, because of this argument, you'll get that in this linear dependency, the coefficient of that new element which you added, that will have to be 0 because you can't write it as linear combination of the other things. But then that would show that the set we got previously, that itself was linearly independent, which is not true because it was maximally linearly independent by SR.
yes.
Okay.
So it must be spanning.
Okay, so then what you're saying is that 2 implies 4. Nice.
And okay. And for 4, we can't add in another element because its span is the whole thing. So any new element we add would be linear combination of other elements.
Yes. Okay, true. So we have 1, 2, and 4 are equivalent. We just need to do 3.
So 3 is basically saying first it is obviously spanning, right? Because of powers.
Yeah.
Then you have to show that it is uniqueness implies the
Yes.
Okay.
So in particular for the 0, for v equal to 0, what uniqueness, we already know that 0 times v1 plus 0 times v2 plus blah blah blah, this thing is equal to 0.
So we want to show that nothing else, we are given that nothing else sums to 0.
Exactly. So it is linearly independent as well. So now we do have that 3 implies 4. Or like 3 implies any of these, whatever.
Yes.
So now we need to show that one of these 3 things implies 3.
And all these implies spanning, so we have to show that one of these 3 things implies uniqueness.
Yes.
Or in other words, one of these 3 things implies there's exactly
I
one
mean,
way of representing 0.
notice that over here, like uniqueness just talks about linearly independent. So
Yeah,
you
yeah.
probably want to
Uniqueness just means there's exactly one way of writing 0.
Yes.
And one way of writing 0 means one of the ways is 0, 0. So any other way would mean not linearly independent.
Yes,
And
exactly.
we are given it's linearly independent. So
Yes, exactly. So if over here, if it were not to be linearly independent, and it is what? Yeah. Okay. If it was not to be linearly independent, then there
then we
is some
could write,
dependency, and
write 0
for that
multiple ways.
equation, that contradicts the condition.
Yes.
Yes, you're done. Okay, so did others follow the proof for all of these things?
Can you repeat it once?
Yeah. Yeah, sure. Okay, so for 1 equivalent to 4, first of all, to prove ki 1 implies 4, we have that this set is spanning V. That condition is given. We want to prove that it's linearly independent. So if it were not to be linearly independent, then you can just take the dependency of that set. Like assume ki it satisfies A. So then you take the dependency, which is like lambda 1, where okay, I erase it. So it's something like this. And we want to show that we can remove one of these elements and the span will still be V. But then one of these things is 0, so it's non-zero. So suppose that lambda 1 is non-zero. Then we get that V1 is equal to minus of lambda 2 by lambda 1 V2 plus lambda 3 by lambda 1, and so on. This condition will just get if we bring things over to, like if we just bring V1 to the other side and divide. And then what this means is that if we just remove V1, so V1 is equal to alpha 1, alpha 2 V2 plus blah 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 plus alpha and Vn. So if we are to remove V2, V1 from the whole thing, even then, if we have something like this, V1 plus blah 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 plus lambda, we want to show that even if we remove one element, the span will still remain the same. So then, if over here, like this thing is clearly a subset of this. I guess that's clear because you just need to add a 0 times V1 plus whatever was over here to write it as linear combination of these things. So now if you have an element over here, then we just substitute the value of V1 and then we will get it in terms of V2 and V2, V3 and till Vn. If we just substitute the value of V. So then we'll get that these two values. Okay, does that make sense?
And in infinite sets, infinite basis is 2 implies 4 as well, right? 4 does not imply 2, but 2 implies 4 even in infinite.
Okay, 2 implies 4 even in.
2 implies 4 and 1 implies 4.
No, I think all of these should hold even infinite, probably.
In infinite, 4 is not implied. Maximally linearly. Linearly,
Yeah, I mean, this same argument still holds, no?
yeah, 4 no.
That if it's not a basis, then you can just add another element to it. You can still do.
No, I mean 1. Sorry, 1 will not work. In infinite.
Okay, 1 implies 4, you said it will not work.
One,
No.
1 implies 4 works, but 4 implies 1 does not work.
Okay, interesting. No, it still works.
How does 4 implies 1 work in infinite?
Okay, yeah, and anyway, I'll go over the 4 implies 1 case again. So then you have, if you have that it's a basis, we need to show it it's minimal, like it clearly spans B. So now, in other words, if you have the basis and you remove one of the elements from the basis, then let's say you remove V1, but then V1, so then we need to show span of V2 and so on till Vn.
No, infinite.
Okay, 2 and so on is not equal to V.
Yes. That's what you claim. I don't believe that.
Okay, sure. But then how does V1 belong to this thing? It can't, right? Because if it does, then notice that the span, we defined it as the union of the span of all the finite subsets. Okay, so this V and S and E, it's infinite. So it's the union of the span of all the finite subsets. So like if it's in the span of the whole thing, that has to be in the span of a finite subset.
Oh, yes.
So then we'll be done.
Because it's about million.
Yeah.
So is it so we can make infinite vector, we can make vector spaces without a basis then?
Without a finite basis.
Without any basis. Can't we make vector spaces without any basis? No, that won't work. At the input.
No, I'm told that.
I mean, we can, yeah, that basis obviously exists because we have a set which oh no, it does not obviously exist.
Yes, it does not obviously exist. So I'm told that, okay, so if you do assume maximum of choice, which most people do, then, so like we said, maximally linearly independent is equivalent to basis. So what that's also saying is that we first pick an element V1. Then we look at the span of V1. And then we just take another element which is not in the span and we put it back and we put it into that set.
Yes, and we can just keep on doing that. Yes,
And we keep going.
that should work.
Yeah, so that just works. But to keep on going, and the reason you need axiom of choice is that at
Ordinals.
every.
Yeah, you can just keep on. I get it from you. I understand.
Yeah, so you need axiom of choice because at every step you're making a fairly arbitrary choice. You're saying pick another element. But if there is no, so what the axiom of choice gives you is it gives you a choice function which is well defined.
Yes.
So it tells you that to choose it need not be arbitrary. There's some rule which lets you choose. So the problem with doing it without the axiom of choice is that suppose I tell you this, you keep doing this algorithm and you'll get the basis. So then what it means for you to really know, for me to have told you, is that if someone else asks you, gives you an element and asks you, is this there in that set? Then you should be able to then you should be able to answer with certainty. But if you don't have the axiom of choice, then you cannot be certain because I told you to make arbitrary choices. So it doesn't. So yeah, you need axiom of choice. I'll not go there into a lot of detail. But I mean, think about it.
I understand how you can do it.
Yeah, okay. Okay. So we have 1 implies 4. Now we need to do turn. two equivalent. One equivalent to 4 we have. Now what two equivalent to 4? So linearly independent is there in both. That's what 2 implies 4. Linearly independent is given to us. We are just given that it's maximal.
Adding the element will make it non-linear.
Yes. So suppose it is not a basis. So it satisfies the linearly independent part. So there is some element which is not in the span. So it just B. This does not belong to span of V1. So till Vn. But then you can prove that V1 and so on till Vn. Also all these proofs which I mentioned, they will most probably work for the infinite case as well. I've not worked it out properly. Okay, yeah, it will work. I mean, this thing will work for the infinite case. And then you consider this set. This thing, you can show that this thing is also linearly independent. And then, yeah, it's just linearly independent. So then you're done. Because it contradicts the maximality of the set. So also one funny thing over here is that you would suppose that maximally linearly independent, that condition makes sense even for infinite case. But the maximum linear, if I were to say maximum linearly independent set is a
That
basis,
wouldn't.
then that would not make sense.
Yeah, because I was getting confused between minimal
Yeah,
and
exactly.
minimum
So you
maximum.
can add another element to an infinite thing and not increase the cardinality.
Yes, yes.
Exactly. So yeah, maximal turns out to be a little bit stronger
Yeah,
than
yeah.
maximum. It's weird. Okay.
It's distinct, I think. Maximum. It's altogether distinct. Maximum means that no, it's maximum in the neighborhood.
Yes, that's what it means. Yeah. Okay, I mean, to be fair, even maximal does not make sense.
It does make sense. No, you
Like,
can just
in
use axiom of,
reality, it doesn't make sense.
you can just use axiom of choice.
Okay. Why do you need axiom of choice?
I mean, with axiom of choice, it's very easy to construct a maximal set.
Okay, sure. Yeah, to construct, you can do that. Okay, anyways, it's 5:30. Let's do this. It shouldn't take a lot of time more. So for 4 implies 2, now we have to do. So if it's a basis, then we need to prove it's maximally linearly independent. So the linearly independent part is given to us. And then we want to show that we cannot add another element without making it linearly dependent. But then if we add another element, that already belongs to the span of all the other things. Because the basis is spanning the set. The basis is spanning V. So then that already gives us the dependency equation if we are trying to add another element. Okay, I'm being kind of sketchy over here. Not being very rigorous. But hopefully you get the general idea. And okay, now let's do 3 implies 4 properly. Okay, so
I think the axiom of choice is not coming from the choosing. The axiom of choice over here would be because you are choosing using ordinals, right?
why do you need ordinals to choose?
Matlab ki we are not we could just choose for finite number around say. We have to show that we can choose for any number, right? Any cardinal thing. And for that we have to use ordinals.
No,
Right?
no, we don't need to use ordinals.
We do.
Oh, yes, we do. We
Yeah.
do.
And that's when the axiom of choice comes in because for you need that axiom of choice for some
Yeah.
ordinal stuff.
Yes, you do. Okay. Okay, so we need to prove that 3 implies 4. So first of all, we know that it spans V because of this condition. This directly gives us that span. If 3 is true, then the set spans V. That much is given to us in this. Now we need to use uniqueness to show that it's linearly independent. How would you do that? So suppose it is linearly dependent. I mean, with linear independency arguments, there's sort of only one thing which you can do, and that is proof by contradiction. Because there's no good linearly independent condition. So if it is linearly independent, then that would mean that there exists some lambda 1 to lambda n with non-zero, such that the linear combination is equal to 0. But then we also have 0 to v1 plus 0 v2 plus blah blah blah. Yeah, exactly. So this contradicts uniqueness. Contradicts uniqueness. Okay. And that gives us 3 implies 4. Now, if 4 is true, then how do you prove 3?
Four is true, that means there's nothing else which goes to 0.
Okay.
And that implies 3. Because if
No.
because if two things have the same value, then we can just look at the difference.
Yes, exactly.
And
yeah,
that goes to 0.
yeah, then it works. Okay. So if it's a basis, then suppose that 3 is not true. So we need to prove that there exists unique. There exists unique blah 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 something. So the existence part is given to us because it spans B. We need to prove that it's unique. Okay. So suppose not. So then there's some V such that lambda 1 V1 plus lambda 2 V2 to B, and it can also be written as alpha 1 V1 plus so on alpha n Vn. And we need to show that it has to be like lambda I has to be equal to alpha I for all I. So now what you'll do is you'll take the difference of these things. So you take this. And we just directly subtract these two. So then, since it follows all the usual properties, you'll get that lambda 1 minus alpha 1 times v1, 2 minus alpha 2 times v2, and so on is equal to 0. But this linearly independent implies that lambda I has to be equal to alpha I. Okay, that is another thing. Proved all. Yeah. So does all of this make sense? Go on, speak up. Yes, no, I will clarify some things if it's not clear.
It makes sense.
Okay.
Wait, I didn't get it about how do you get the last part of 4 to 3?
Okay.
Like, I got the subtraction, and then you said, how do you get like lambda I equal alpha I?
Yeah, so we know that, what did we do? 4 implies 3. 4 was basis, right? Okay, so we know that it's linearly independent. So if the linear combination of some things is equal to 0, then that means that all of those things have to be equal to 0.
Oh, right, yes.
Yeah, so lambda I minus alpha I equal to 0, and you can add alpha I to both sides. Okay, nice. Okay, cool. So if there are no questions, I'll stop the recording for now.
You said you were going to show the cardinality thing.
All right, what was I going to show? Oh, the
Uh,
cardinality thing. Bases, the cardinality of bases are equal. Right. Okay. So the result is that
there's a projection between any two sets of bases, right?
no, okay. Actually, I will not be doing cardinality. I'll just be doing it for the finite case.
So you're not doing any nice bijection thing.
No, sadly not.
So
Okay, if I wanted to do bijection, then how would I do it? Okay, no, I'm not going to do a bijection thing, sadly.
um
So I'll just do it for the finite case.
oh
Yeah, I don't really know how to deal with infinite dimensional things, but I'll maybe some modified version of this argument works. Let's just go over this once and then we can try to see where it
can be
really
generalized.
needs the finite part.
Hmm.
Though I think it needs it very significantly. Okay, so if these are two different bases, then we need to show that m is equal to m. What if these are two bases? Okay, so to do this, the argument is that we'll systematically
do you
keep.
want to give this as homework, maybe?
Okay, it is kind of late, so
I'm okay
we-
with extension.
okay. I guess we'll have a vote. Fine, just raise your hand if you want to see the proof now, or do you want to try it as homework? Raise your hand if you want to try it as homework.
Um,
Okay, sure, we'll. Okay, fine. Yeah, you can try it as homework then. It's a nice argument. Let me stop.